Okay, let's see, make sure. Good, it's recording. All right, so what we're going to talk about in the next couple of sections are some power functions, right? We've already looked at the quadratic. We know how to graph quadratics that open up, down, they move left to right, they're compressed or stretched, and they're flipped over the x-axis, right? So we can do all that. And in so doing, we gathered together a bunch of translation and reflection results. Those are applicable to any class of functions we have. And so what we're going to do is focus only on the general, like the most basic case of a function in general. So in this case, we're going to look at positive integer powers of x. All right. We're going to learn how to graph that, and then by using all of those previous results, we'll have a knowledge of how to graph all of these translations and reflections of those graphs as well. Right, so there was the power in doing those earlier, is that they can actually apply going forward. All right, so in this section, let's look at functions like x cubed, x to the fourth, x to the fifth, so on and so forth. Anytime you have a new function that you don't know how to graph it, the best approach is to plot points, just to get an idea. And typically, the way you want to choose those points is basically you're not going to favor any one input, right? So you look at the domain. Here, there are no restrictions. You can cube any number you want and get a real output. And so I'm going to take values including 0 and equally space them on either side of 0 just to get a feel for what the graph looks like on both sides. And that's what I did here. I took -2, -1, 0, 1, and 2. And if you cube each of those, you get these values in turn. And so if you were to plot the points, you have 0, 0, 1, 1, 2, 8, and then you have the negative of those on the other side. Okay, so the first observation, of course, is that it's no longer U-shaped like a parabola, right? So not all power functions look like U's. And the reason is before the square got rid of the negative on an input. Now, remember, if you cube a number, you're going to, and it's negative, you're going to get a negative output. And so that's what's going on here. What would have been up here before is now down below in the third quadrant. Okay, so this is a typical cubic function. All right, so now what would happen if we looked at other functions like x to the fourth, x to the sixth, and let's say, how do they look? All right, so let's look at values again. Right, so I'm taking a whole bunch of values. All of these power functions that we're looking at are polynomials, and there are no restrictions. You can always raise any real number you want to a positive power, and it'd be perfectly well defined, right? And so, a positive integer power, pardon me. And so here, all of these numbers are in the domain. Notice I equally spaced them on either side of the origin, and I took values between 0 and 1 and 0, -1 purposefully because I want to see what happens for values that are between 0 and 1. Does it get bigger? Does it get smaller in terms of the output, right? That'll be an important observation to make. So here you could check if you want, but I just compute the square, the fourth power, and the sixth power of all those inputs, and these are the values that I get. The couple things to notice is that the points 0, 0, the point 0, 0 is always on the graph. So these graphs all pass through the origin. The point -1, 1 and the point 1, 1 are always on these graphs. Okay. And then here, if you look at numbers between 0 and 1, the larger the number is, right? The larger the number is, the larger the output. So that's fine. But notice that if you square or raise it to the fourth, if you raise that number here to a larger power, the result gets smaller, right? And so these values are going to be kind of smaller than what the corresponding input would be. All right, so if you graph them, this is kind of what you get. The x squared graph is just this general sort of, I don't know, aqua type graph. X to the fourth is a little bit steeper when you get beyond 1, right? It grows faster. But with respect to numbers between 0 and 1, raising a half to the fourth power resulted in a smaller number than did squaring it, right? And so that's actually going to be below x squared on that particular interval. And then x to the sixth is even worse, right? It grows even faster beyond 1 and -1. but it's going to be smaller, lower than the other two graphs between 0 and 1, because we're raising a number to a number between 0 and 1 to a higher power results in a smaller number yet. All right. That said, though we do have these subtle differences, they all generally look the same, right? They all are U-shaped. The higher the integer power, the flatter it gets between 0 and 1, and the quicker it rises beyond -1 to the left and 1 to the right. These are all even functions, right? If you put a negative x in for each of these, you'll get just the same result as if you just put the x in, because the negative goes away with the even power, right? And so this is what you want to take away. All of the positive integer even powers of x look like u's. The higher the power, the flatter it is here, and the quicker it rises, beyond 1 and -1. All right, the same will hold true with respect to x to the 5th and x to the 7th if you compare them to the x cubed graph. All right, so I look at the same table of values. The exact same phenomena is going to occur between 0 and 1 and 0 and -1, right? Raising a number between 0 and 1 or 0 and -1 to a larger integer power creates a smaller number than raising it to a smaller integer power. All right, and so they're all going to look, if things were going to happen the same way, we'd expect these graphs all to look like x cubed, but to be flatter between -1 and 0, -1 and 1, in other words, closer to the x-axis comparatively, and then they rise quicker to the right of 1, and they dip down to -infinity quicker to the left of -1. That's what you would expect to have happen if the same sort of reasoning as was used here applies. All right, and indeed it does, right? So if you were to graph these on your graphing calculator or some similar such thing, you would get these sort of cubic graphs the way I described. Notice the other thing to notice here is that they're all odd. They all have symmetry about the origin. Okay, so let's look at example 1. We have a class of functions now. We know what all positive integer powers of x look like. They're either u's or they're cube graphs. Okay, so now we want to use upon all the tools that we had from our toolbox in the previous chapter, including the translation and reflection results, to understand more complicated versions of these graphs. And so what we'll do here in example 1, we'll walk through step by step an even power, and then in the corresponding your turn, you'll do the same thing with an odd power. All right, so let's talk about these. First, for part 1, you want to explain how the graph of f of x can be obtained from this graph using the transformation results. Okay. Well, remember, if you always start like you're using the order of operations. So we start with an x. The first thing you do is you add 1 to it. But if you add 1 to an input, you're going to shift it to the left 1 unit. Okay, so we're taking x to the 4th and moving it left 1 unit. And then if we subtract 16 from that whole thing, then we're going to move that whole thing down 16 units. Okay, so left 1, down 16 units. That means that since this looks like a U, remember the even powers look like the parabolas, the vertex is going to be at that new point, namely at -1, -16. And we know that since there's no negative multiple out in front, it opens upward. So that will be a local minimum. All right, that's what I was getting at here. So what is the range? Remember, the range of a function is the set of outputs that are retained, all the y values that are retained on the graph. And so here, we know that since that's the vertex and it opens upward because there's no negative multiple, -16 is the lowest y value, and then the range extends up to +infinity. And so the range is this half closed interval from -16 to infinity. For 3 and 4, let's think about what these intercepts mean again. The y-intercept would be obtained when you plug in 0 for x. Remember, on the y-axis, that's the vertical axis, x is 0, right? And so that's the easiest one to find. You plug 0 in for x, that gives you 1 to the 4th, which is 1, -16, that's -15. So your y-intercept is 0, -15. Okay. For the x-intercept, or intercepts, if they exist, we want to find when this whole thing is equal to 0. Remember, on the x-axis, the y is 0, but f of x itself is the y. That's the output. So we're going to set this equal to 0, and we're going to solve it for x. So let's do that. All right, so you're going to use basically the old radical method that you would use for solving quadratics. But now we're not taking a square root, we're taking a different index root. But it basically does the same exact thing. So I'm taking the 16 to the right. I want to get at the x plus 1, so I need to get rid of this fourth power. We know that a way to get rid of the fourth power from our radical section is to take the fourth root of both sides. But remember, when you're solving here an equation involving roots, anytime you take an even indexed root of both sides, you have to put plus or minus, because remember, this even power would have killed off a negative inside, right? And so the inside could have been negative, and that would have given you a perfectly fine solution to that equation, right? So anytime you're taking an even indexed root, so fourths, sixth power, eighth power, whatnot, put a plus or minus. We know that the fourth root of 16 is 2 because 2 raised to the fourth power is 16, right? So the right-hand side simplifies 2 plus or minus 2. And then to find x, you subtract 1 from both sides, and then realize that you're getting 2 solutions here. Negative 1 plus 2, which is 1, negative 1 minus 2, which is negative 3. All right. Notice that those x values they straddle the vertex equally on both sides. That has to happen because the function's even, right? You have to be able to reflect, not even, it's symmetric about the vertex. And so you have to be able to reflect it over the vertex to get those values. All right, remember the vertex was at negative 1, negative 16. So it's this vertical line that it's symmetric about. And so it would make sense that these are equally distant from negative 1. All right. We are asking on let's see, so sketch the graph, we did that. On 5, or 6 rather, we want to know what's increasing, decreasing, and then we want to find an interval where it has an inverse. Okay, so let's take a look. To the right of the vertex, it's going up, right? So from negative 1 to infinity, it's going up, so it's increasing. Back the other direction, it's decreasing, okay? For an inverse, the function's not 1-to-1, right? It's horizontal, or sorry, it's not horizontal. It doesn't pass the horizontal line test, and so it's not 1-to-1. And so it does not have an inverse on the entire domain. The one thing that you can do, it's in the manual, but we did not talk about it in the previous lecture, only because I didn't want to talk about it until it came up in context. And so here, if you look at the vertical line through the vertex, so at negative 1, negative 16. If I stay only to the right of that line, I get an entire half of this graph, and it basically tells me what the other half looks like because I know it's symmetric about that line. And so for the purposes of finding an inverse, if I restrict my attention to the right of negative 1, so I forget about this part of the graph, then that function is 1-to-1. The restricted function is 1-to-1 in that interval, and so it has an inverse, right? That'll give me the positive root that I want. The other side would give me the negative one, all right? And so here, if I make that restriction, I'm going to go through and solve this equation for x like I normally would, right? So I'm undoing the process. So you follow basically the same thing that we did when we solved this equation when I plugged in 0 for y, right? It's no different. It's just now instead of a 0 here, I'm going to have a y. Okay, so if you compare this, oops, if you compare that to this, you'll notice that. All right, and so what I did here instead is okay, so the other approach here, sorry, I'm mixing them up between sections. What we had done before is we solved this, excuse me, for x. And here what I did was I switched the x and the y. The only purpose that this serves here is that in the end, you already have a function of x to consider. So I don't need to change the variable at the very end, right? Remember, what we're really doing here is using the fact that to get the graph of an inverse, you literally switch the x and y of the points. And so I'm literally doing that algebraically here as an extra step. If that confuses you, just start with this guy here and solve it for x in terms of y, right? It'll give you the exact same function in the end. It just now instead you'll have a y here and an x. All right, it's exactly the same formula though. All right, so if we go through that process, you'll get the same sort of thing that we had before, but now don't forget, we restricted our attention from -1 to infinity for the output. And so we're going to use the positive root here for our inverse. Okay. All right. All right, so go ahead and try this your turn now. All right, so you have the same sort of thing. It's a cubic. It's been translated and whatnot. So same questions. You want to discuss how to obtain the graph, what the range is, x and y intercepts, does it have an inverse, and graph it. See what happens. And we'll talk about it when you come back. Okay, so let's look at it. So to get this graph, we're starting with x. We're subtracting 4 from it, so I'm going to move it to the right 4 units. The coefficient of 3 here is going to make it rise that much quicker, so I'm going to compress it. It's going to go quicker up. So I'm going to compress it by a factor of 3 toward the y-axis, so I'm going to stretch it. The negative reflects that graph over the x-axis, and then adding the 1029 to it. Remember, if that confuses you to put it in front, just tack it on back here as a plus 1029. It's exactly the same thing. That'll move it up that many units. Okay, and this here is a typo. This should be 1029. Okay, all right, good. The range, well, the range of any cubic, if you remember, went from plus infinity to minus infinity. Moving it left or right or up or down or stretching it doesn't change that, right? So the range is going to be the same for all cubic, and in fact for all odd integer powers of x and their translations and reflections, the range will always be all reals. The only time you have a range change for power functions is when the function happens to be an even power of x. The y-intercept, if you plug 0 in for x, that's what I do here. Right, you get 1221. You can check that out. Just plug 0 in for x. That's the key here for a y-intercept. To find an x-intercept, you want where the y value is 0. In other words, the output happens to be 0. So I do like I did before. I'm going to set this equal to 0 and solve for x. So to do that, I'm going to take this guy to the right. I'm going to divide by 3. And now I want to get rid of this cube. But remember, when you take an odd indexed radical of both sides, you do not put plus or minus, right? You only do that when you have a positive or an even root, because the even would have killed the negative. The odds don't kill the negative, right? So you don't put a plus or minus here, right? So you get a cube root of 343. We know that's 7. And so when you add 4 to both sides, you get 11. So there's only one x-intercept this time, which makes sense for cubic graphs because they're 1 to 1. You get 11, 0. All right, and then to find the inverse, you do exactly what we did here, but you replace the y by a 0. Okay, and so that's what I did. And here again, I'm switching the x and the y, right? If typically that's what people do in terms of the high school approach and whatnot, if you've seen this before. But again, you'll get the same formula at the end. So I'm just going to follow this so I don't have to change it on the screen. You switch the x and y, and you solve now for y. So I'm subtracting the 1029, dividing by the -3, right? Then I'm taking care of this negative just so I don't have all these negatives running around. I remember, if you have a negative in the bottom of a fraction, you can move that negative to the top and then distribute. So that's what I did going from here to here. You don't have to do that. It's just cleaner if you do. All right, once I'm here, take the cube root of both sides, add 4 to both sides, and there is your inverse function. Okay. All right. Example 2 and example 2 and your turn 2 are just kind of more of the same of what we've seen before, but just now applying them to a broader class of functions. right? So before we had mentioned that you'll want to find intersections of functions, especially in Calc 2 when you try to find areas of curves, right? And so we want to get used to doing that. So here we just ask a simple question of when does the cubic graph and the basic quadratic graph intersect? When do they intersect? For any two functions, I don't care what you put in here for x cubed or x squared, no matter what those functions are, to find where they intersect, you simply set them equal to each other and solve for x. Right? So the solving for x part is sometimes easier said than done, but in this case, it's not bad, right? You take everything to one side, you factor out the x squared, and then we know that one of those has to be 0 in order for the equation to be satisfied. Either x squared is 0, well, the only way that happens is if x itself is 0, or x minus 1 is 0, which means x is 1. All right, so if you plug either of these back into the original functions, you get the actual points of intersection, namely 0, 0, and 1, 1. Right, I'm literally plugging in 0 for x to get 0 each time, and then 1 for x to get 1. Okay. For your turn 2, you've seen this difference quotient before, right? We've seen it for different functions earlier, particular quadratics and linear functions. Now we're just throwing a cube in, right? So the only hard part here, or I should say tedious part, not hard, tedious, is the algebra, right? In particular here, you have to be able to compute f of x plus h correctly right off the bat. And so to do that, you could actually, why don't you stop actually and try it and then come back for the discussion. So I'll pause for a moment, pause the video, do it, and then come back. All right, so here, if you remember, if you put an x plus h for the x, you'll have a 2 times x plus h like I have here, and you'll have minus x plus h cubed, right? That's the first part here. The thing is, remember, you do not just cube the x and the h, right? That's the biggest algebra no-no that I see at this point, right? You have to actually multiply this out. And so remember, x plus h quantity cubed is x plus h times x plus h squared. I need to FOIL this out. First, outer, inner, last. That's how I'm getting this term here, or expression rather. And then you have to distribute x through those 3 terms. That's what I did here. H through those 3 terms. That's what I did here. And then you add like terms together. Right? So x plus h cubed is actually this expression here. All right. So what do? I plug it in right here. And then to simplify the top, remember, you can't just kill this h with that h and call it a day. You have to distribute the 2 through, the negative through all 4 terms, and this negative through those 2 terms. That's what I did up here. Then you can cancel out like terms in the top alone. That's what I did. The 2x and the x cubes go. What remains has to involve at least one h, and it does. All right, so I yank that h out. Right, so I get h times this expression. Those factors of h cancel, and what I'm left with is just what's inside. Right, so this is the end result of that, of computing that difference quotient. All right, so the homework problems they're fewer this time, but they involve basically the same thing. Right, you'll notice that number 3, I'm asking you to do the same thing we did before, but now with the 6th power, and then with the 5th power, same sort of questions, same sort of intersection points, and the same difference quotient ideas. Right, so give those a go. Just make sure that everything is firm, so that before, when we go on to the next section with root functions, this is well understood. All right, let it go, or take it, if I can speak. Give it a try. Let me know how it goes. All right, take it easy, guys. Bye.